Not, I hope, a superposition.
No. This time. Yes. Here we are. So my purpose this afternoon is to develop some of the consequences of what I've said this morning. One of the consequences is quite strange and difficult to accept to Western scientists. The problem is that usually when they have a physical theory, they wish to have a view of the world that goes with it. They don't just content with a theory that is efficient, that enable them to predict and to make technology. They want also to have a picture of the world. Einstein was one of these wonderful scientists who dreamt of a grand view of the world. But the problem is that quantum physics has put some obstacles on this way, and that presently there is no view of the world which is both compatible with quantum mechanics and which is uncontroversial, that everybody accepts, every physicist accepts, because each one of the proposed views of the world that fits quantum mechanics has paradoxes, difficulties. Nobody is completely convinced by it. So my proposition is that maybe we have to accept that this physical theory provides us no view of the world. So,
view of the world. View of the world.
I think in Sanskrit you would call that. In Sanskrit you would call that drishti. Drishti, isn't it? Now I want to come back to basics, really to things, elementary things. So, what is science, actually? What is the purpose of science? It could be that science aims at giving us a faithful picture of nature, that it is a mirror of nature. This conception comes in two varieties. The so-called realist varieties, according to which a theory, a scientific theory, is a faithful representation of reality as it is in itself. This is the ultimate dream, in fact, of Western scientists. They want a picture of reality out there, but as it is in itself. The second view is more modest. It says, yes, a scientific theory is a picture of the world, but not a picture of the hidden world. A picture of the manifest world, the world which is visible, empirical world. And so empiricists say that good scientific theory is just a faithful summary of observed phenomena, not more. It's still a picture of the world, but a picture of the apparent world, not more. The second view of science is the other way around. It's not as if we were, so to speak, capturing nature in our nets, but it's us who are superimposing our concepts and our views on our image of nature. Kant was one of the proponents of this idea in Western philosophy, with some nuances, but I think I would skip nuances. The third possibility is what I would call here a middle way. It's, a scientific theory in this way of seeing it is neither a picture of nature, not just a superimposition of our own minds. It's the byproduct of an interaction between us and nature. It's the expression of an interplay between us and nature. And Francisco Varela developed such a view under the name of enaction. It is the theme of his wonderful book, Embodied Mind. according to him, there is no way of putting foundations, of saying that, in fact, we can ground our view of the world somewhere. There is what he borrowed from Buddhist thought, namely dependent arising of the knower and the known. So the interplay is what science gives. For instance, science can give us methods to behave adequately and efficiently in the world, namely to relate with the world in a very clear and efficient and powerful way. Nothing more. And so in that case, a scientific theory is only an instrument for us to orient in the world and use it in a mode which is useful for us. Now, second part of the basics. What is a physical theory? Namely, what is a scientific theory that bears on matter? Well, in fact, in the history of Western thought, there were at least 4 conceptions of what is a physical theory. The first, the oldest conception, was the conception of Aristotle. He said that a physical theory is a statement of the first causes of every phenomenon. The first causes, namely, you cannot go beyond them, according to him. It's quite unlike Buddhism, because in Buddhism you can always find another cause which causes the cause, and so on and so on. But according to Aristotle, there was a first cause, and full stop. And physics should look for this first cause. It was also, physics, according to Aristotle, was also meant to find the essential properties of things, the properties that are most intrinsic. Okay. But after a certain time in which this theory of theories was very much accepted, throughout all the Middle Ages it was accepted, people started to see something artificial in it. For instance, when somebody wanted to explain the virtue of the opium to bring sleep, he said, I can explain that by saying that opium has the essential property of being sleepy, And this sounds quite artificial. Okay, it gives sleep because it is sleepy. Okay, so people like Descartes, René Descartes, the French philosopher, said that this was indeed completely artificial and that you had to explain everything in terms of mechanical interaction, bumps of bodies one into the other, primary qualities, as Arthur told us, namely spatial qualities, extension, velocity, and full stop. Even the qualities, for instance, of the virtue of opium to bring sleep had to be explained in terms of motion of particles. This is what Descartes called a mechanical explanation. Among many other things, Descartes wanted to explain gravitation by way of bumping of particles into each other. For instance, he said that the gravitation was due to the fact that there was a surrounding of subtle matter that bumped into the Earth or bumped into us and pushed us towards the Earth. But then came Newton, and Newton went much further than Descartes on the plane of mathematical description of phenomena, but he had to relinquish any explanation of the type of Descartes. He didn't try to explain gravitation by means of bumping of particles into the Earth or into the objects that fall onto the Earth. Newton renounced explanation, mechanical explanation of gravitation, and he just posited a mathematical law. This mathematical law was amazingly efficient to predict everything. You could predict all the motions of all the planets for 100 and even 1,000 years, and you were perfectly exact. Yet he had no explanation of gravitation, only a mathematical law. So apparently you have a sort of regression here. Before we had an explanation, and now with Newton we have no explanation. But we have a much better descriptive mathematical theory and predictive mathematical theory. Now, according to Bohr, quantum mechanics, for instance, is a good case of that. Physical theory is not even a description of phenomena. It's only of phenomena as they occur by themselves in nature. It is only a predictive tool, mathematical predictive tool, in order to predict what? Experimental event in the laboratory or technological event that you could deal with in your laboratory also, or in your workshop. Okay, so you see a sort of progressive decrease of the scope of theories, but a progressive increase in their efficiency. This is very fascinating. The more the theories are efficient, the less they pretend to make us understand the world as it is. Okay, now let's understand another point, another pedagogical point I want to make. It is often said that the interpretation of quantum mechanics is a problem. We don't know how to interpret it. So what is the difference between a theory and its interpretation? Now, a physical theory basically is a mathematical framework, especially according to Newton or Bohr, a mathematical framework to describe or predict phenomena. It is made of laws that connect variables. What is a variable? It's a value of a measurement. For instance, you can measure length, or you can measure velocity, and the value of the length you have measured is a variable. The value of the velocity you have measured is a variable. So a physical theory is made of laws that connect variables. For instance, classical mechanics is exactly of this type. It says this, a law of classical mechanics does the following job. It says, if you know, because you have measured, that position of this body is p0, and velocity is v0 at initial time t0, then under certain circumstances, you can calculate that the position and the velocity will be this and this later on. For example, if I tell you, okay, I've thrown this ball with this velocity, for instance, 10 kilometers per hour.
Speed, yeah.
Yes, the speed, okay. Yes. And then I throw it out from that point at the top of this tower, this metallic tower. Yeah. Okay, if I throw it at 1.5 kilometers per second, it falls quite straight away towards the Earth. You can predict it with Newton's theory. But if I throw it much more quickly, then it becomes a sort of tour around the Earth. It becomes an orbit, you know. So here again, Newton's theory can predict that and describe the trajectory of the ball around the Earth. This is why it is so powerful and efficient. Now, okay, let's try to flesh out this mathematical skeleton. Namely, what is the view of the world that comes with this wonderful predictive and descriptive mathematical tool that enable you to predict the value of velocity and position from another value of velocity of position? In fact, there are many views of the world that fit that theory. There was the old view of the world of Newton, according to which the world is made of material bodies endowed with velocity and position. But there is also an alternative view that was formulated in the 19th century, which is completely different, which said, in fact, the world is not made of material bodies. In fact, the world is made only of energy. And sometimes there is a concretion of energy somewhere, and it gives rise to the appearance of a material body. This view was formulated by many scientists at the 19th century. Therefore, there are two conflicting views of the world that nevertheless fit the mathematical skeleton of Newton's theory. So you see that there is a difference between a physical theory on the one side, which is just a set of mathematical laws, and its interpretation, which is a view of the world. There can be many views of the world that fit this one mathematical skeleton. Okay, so this was the case with classical physics. It was no difficulty, actually, because each one of these views of the world fitted perfectly well, no problem. Only their multiplicity was a problem, because why many rather than one? Now, what is quantum theory? Next question. Oh, okay, I will skip the history because it would be long, but I would like just to tell you that in fact quantum theory is simple and understandable. Maybe that means that I don't understand quantum mechanics, but no problem. I accept that. Quantum theory is only a mathematical scheme to predict measurement outcomes with certain probabilities. You have, for instance, in quantum theory, a symbol which is very well known, the symbol psi, which was actually the wave function according to Schrödinger. So you have this symbol psi, but it is used for only one purpose. It's to calculate the probability of finding one event. Now, once you have the initial function psi, then this initial function psi enables you to calculate the probabilities of the measurements at time 0, namely initial time. But you need also an equation that gives you the same predictions, not at time 0, but at a later time. And this is called the Schrödinger equation. Then, the Schrödinger equation modifies the psi function and turns it into another function that enables you to calculate the probabilities of the measured phenomena at time t. That is all that is to be known of quantum mechanics. Everything is in it, only the mathematics is missing. Okay? So,
His Holiness is wondering whether you've actually simplified it or made it more difficult.
I'm sorry.
Yes, okay.
I made it as simple as I could, but of course, it's quite difficult to go further, I think. Now, there are many interpretations.
Just to go back, so your claim is that quantum theory is what? The essence of the quantum theory is simply this equation?
Yes, yes, exactly that. It's just, you know, a psi function that enables to calculate probability and an equation of evaluation of this psi function that enables you to calculate the probability not only at time 0, but also at later time. And that's it. Nothing more to quantum theory.
So am I right in thinking that your claim is that quantum theory makes it possible to predict probability outcome not only at a specific time, but also
at later time.
A later time.
That's the reason why it is predictive. It can enable us to predict future results of future measurements. And this is why
but
it is so
only in
powerful.
probabilistic terms.
Only probabilistic, yes.
No. Probability
So this is all what there is for the mathematical skeleton of quantum mechanics. But now you want a view of the world that fits with it. You want to say, okay, but what is this function psi? What is it? What does it represent? Is it a reality? Is it not a reality? Is it just a symbol that enables us to calculate probabilities? That's the question. And therefore, many scientists try to ask this question. What is psi? What is this mathematical symbol? What is the world made of? Namely, if psi is a description of the world, what is the world? Well, there are three types of answer, actually. Three types. One, I will skip a little bit, but one is that psi is all the reality. In fact, all the reality is made of a wave, which is described by psi. Schrödinger, the inventor of the Schrödinger equation, thought this way. He thought that, in fact, there was nothing else than the wave. So, now, many other scientists, present scientists, believe the same type of thing. For instance, the Everett interpretation is very much similar to that. But I skip that. I don't care about that.
So if you look at sort of the cosmos from a vantage point of view, like in the image, say, for example, if you look at the Milky Way, there seems to be almost like a kind of a wave pattern there.
Yeah, absolutely right. Yes. Now, of course, this wave of which we are speaking is not a visible wave. That's the point. But it is an inferred wave that enables us to calculate many things. And therefore, since it enabled us to calculate so many things, Schrödinger believed that it was, in fact, an adequate description of reality, and therefore that reality was wave-like, was made of a deep wave, invisible, but causing many effects. The second interpretation is that, in fact, the psi function is just a mathematical symbol, nothing more, and it's just here to make us calculate the probability of presence of particles. And therefore, only particles exist, and psi is not just a mathematical symbol. So either the wave is all the reality, or the particles are all the reality, and the wave is just a symbol. And also there is a mixed conception, which was typical of De Broglie and Bohm also. Which said that, in fact, there were the two things, half wave and half particle. That the particle was, in some way, taken by the wave, it was piloted by the wave, and therefore the wave was used by the particles to guide itself through the world. So you have these three interpretations. These three views of the world. Either the world is made of a wave, either the world is made of particles, and in fact the wave is just sort of mathematical symbol, and either there are two realities, half wave and half particles. Now, these three views of the world offer a lot of paradoxes. If you try to stick to them, you land into a lot of paradoxes. I just skip the paradoxes because it would be too long and too complicated. I just realized it. But maybe there is a fourth possibility. A fourth possibility. This possibility is very challenging, but I offer it to you. It's that quantum theory says really nothing of the world. Nothing of what the world is or is not. It just offers us a tool in order to orient ourselves by probabilities throughout the events that we meet or the phenomena that we meet in the world. Of course, it seems very counterintuitive. Quantum theory is an amazingly efficient theory. Everything here is based on quantum mechanics. Many elements of this computer are based on quantum theory. There are lasers. There are so many things that depend on quantum theory and that are so powerful. How is it possible that a theory that is not describing anything of the world is so powerful and efficient? It sounds strange, but I offer you a comparison. Let's take, the insurance companies. Insurance companies must know how many accidents there will be during the years to ask people the right amount of money to insure themselves against the accidents. Now, how do they do? Do they know which accident you will have next year? Obviously, no, not. They don't know the nature of the accidents you will have next year. But they use a powerful tool which is called statistics. And with this tool, which says nothing about the nature of the accidents, yet they are able to predict the number of accidents, approximately, of course, during the next years. it could be the case that quantum theory is this kind of theory, which is very powerful on the statistical level, and yet very weak on the descriptive or explanatory level. Okay, well, Heisenberg and Anton Zeilinger also were two people who were very close to this position. According to Heisenberg, you cannot say by means of quantum mechanics what happens in the world independently of your intervention, of your experimentation, of your observation. You can only say what will happen with a certain probability in the laboratory when you will observe it. And therefore, the verb to happen, according to Heisenberg, the verb to happen is restricted to the observation. Nothing more. You cannot say more. You cannot say beyond anything beyond observation with quantum theory. According to Anton Zeilinger, who should have been present actually, quantum mechanics is a theory of the limits of available experimental information. It's not a theory of what the information is about. It's just a theory of information itself, nothing more. So, playing with words, I wish to offer you an attempted, very daring interpretation. Maybe quantum theory has revealed us that nature has no intrinsic nature. Maybe it's the true revelation of quantum mechanics. It's not a revelation about the nature of nature, but it's a revelation about the fact that maybe the nature has no intrinsic nature. This is a possibility. Now, this is a deep problem with Western culture. So this is a very great challenge for Western thought. Western physicists have a tremendous difficulty to accept such views. They don't even consider that, very rarely. I could quote only two physicists, and most other physicists are very much against that. For instance, people say very harsh things against these strange physical theories, such as quantum theory, that apparently has no way to show us a view of the world. For instance, according to Isabelle Stengers, a Belgian philosopher, many physicists think that quantum theory has betrayed the ideal of science, because the ideal of science was to reveal the nature of things, whereas here it's silent. It cannot say anything, just say probabilities of events. René Thom, who was a French mathematician, was very, very aggressive against that. He said, in fact, quantum theory is the scandal of our century because it has betrayed the ideal of science. It's terrible. Okay, now my personal view is that we must be quite prudent. Namely, should we go on with the ideal of science, even though it brings so much paradoxes, or should we drop the ideal of science, provided it gives us some clarity? That's the two options, I think. If the dream is suspended, much clarity comes. But of course, the dream was so dear to so many of our French scientists. Now, I think for Buddhists, it should not be a problem. For Western scientists, it is, but for Buddhists, it's not. Because, first of all, I would like to insist on the fact that maybe the reason why quantum theory is so powerful is precisely because it's not specific about anything. It's because it's so general. It covers all sorts of events in all sorts of domains, just calculating the probability of these events. One has showed very recently, it's a very recent work, 2 or 3 years ago, that quantum theory can even be applied to human sciences. It can be applied to linguistics. I could explain that to you later. it can be applied to semantics very efficiently. It's the same theory, and yet it applied to several domains. Why? What is the common point between microphysics and linguistics? The common point... The common point is that in both cases, you have relational phenomena. Only that. Only common point. Now, from a Buddhist stance, and I chose Dogen, the famous Japanese monk and philosopher. Very interesting. From a Buddhist stance, it's not necessary to go very much beyond what there is, what is immediately given, beyond the freshness of the quality of presence. You can, or you should, just appreciate suchness, tatata, in Sanskrit. What is given, immediately given, and not go beyond. And just describe what is given, maybe, but not try to imagine what is behind the veil of appearances. For instance, Dogen said, this entire universe has nothing hidden behind phenomena. There is no veil, no necessity then to remove the veil to see behind it. Just see the veil as it is present here. And what science does is exactly what Dogen described, namely, unfolding these phenomena in the most profound depth, and therefore be able to describe them in the most precise way, but not go beyond it towards a possible nature of things. Okay, I think I will conclude on that.
Thank you very much.
Thank you.
Wonderful.
Your Holiness, I don't know whether you would like to respond to this, whether you agree with Michel that there is some similarity, some meaningful similarity here between his interpretation of quantum mechanics and the Buddhist philosophical tradition? This seems like a very big and bold claim.
Yeah.
This reminds me, some time back, I think at least maybe 20 years ago, 15, 20 years ago, in Delhi, one occasion, one Indian nuclear physicist, Rajaratnam or something.
Rajaraman.
Ah.
Rajaraman.
Oh. That, his nickname, usually people call India's Sakharov, because he was one of the scientists who built India's nuclear weapon. So, she told me, quantum physics in the world, in modern world, this is something new, very new theory. He found the essence of that concept. He found already in Nagarjuna's text, some writing. So that's 2,000 years ago. That is suchness shares only. Tishini. So the in Buddhism, in particularly the Nalanda tradition, there are 4 schools of thought. So except the Madhyamaka, even within Madhyamaka, there are different sort of concepts. So basically, those are the school of thought which essentially believe something
intrinsic existence.
Intrinsic existence.
So within the history of Buddhist thought, there were, four main primary classical Buddhist schools of thought, and except for one of the branches of the Madhyamaka school, middle way school, all the other Buddhist schools' view of the world, particularly the physical world, was really grounded upon some kind of quest for the ultimate
both physical world
and the
mental world.
And the mental world. Sort of driven by this quest for seeking the ultimate constitutive elementary blocks, which are somehow have an intrinsic existence, an essence by virtue of which they exist. So once you go through that line of inquiry, then eventually you run into all sorts of problems.
Yeah.
So then the fourth Madhyamaka philosophy, so without investigate these things which actually is the effect, these are reality. Okay, it exists. But if we investigate what is the reality of that, then we can't find. So then nothingness. Right. So the appearance due to many other factors. If we investigate the object itself, you can't find. The very nature of the existence of these things are due to other factors, not by itself. So our sort of investigation is focusing on the particular sort of the subject. Right? So since it is very existence is due to other factors, not itself, so we can't find. That does not mean non-existence.
Nothing exists.
Yeah.
Nothing exists.
Yes, exactly.
It is fact. It is work.
Yes.
So then, conclusion kareta, the mere designation.
So then the question is, in what sense can we say they exist? What is the mode of their existence? Then we can only understand in some relational terms or by mere designation. And then another question could be raised. In that case, whatever mind constructs, does that mean it exists?
Any mental objection, mental projection.
Not really.
Does it exist? No.
Then the answer is, of course, no. So not only should it be something that is kind of, affirmed by a kind of a consensual convention, but also that the reference of that convention should not be something that can be contradicted by another valid convention.
Right.
Very similar, the
Very
scientific
similar.
sort of research. One scientist to find something, you will not sort of decide.
Right.
But you see, another sort of repeat
Confirmation,
test to that. And also some other. They all found similar. Then decide that's true. So that are tanya samashan.
So this is what is meant by the second criteria, that it should not be violated or contradicted by another valid cognition.
Right. That's right.
So you got never check the
And then, of course, in the Buddhist text, there is a third criterion added to this, which is that it should not also be negated by an inquiry that searches after the ultimate mode of existence as well. But that, of course, takes us into a Buddhist domain, Buddhist philosophical domain.
Yes.
So, for example, within the Buddhist world, from the Madhyamaka point of view, since many of the postulates by other schools are essentially, arrived at as a result of a form of inquiry that was actually seeking for their ultimate mode of existence.
So, seems, of course, in detail, there are still differences. But broadly, I think the Buddhist Madhyamaka philosophy and quantum physics, we can shake hands. Isn't it? What do you think? Do you think?
I think so. Let's shake hands.
Not that way.